Okay guys, welcome back. Today we are going to be learning a little bit about what science is and how we do science. So you've probably heard this term scientific method before. Our opening question for the day asked you to try to remember what you can about the scientific method. So I feel like there are a lot of, misconceptions about what science is and what it isn't. Some people talk about science like it's a substitute for a belief system or whatever. But today we're going to learn that all science is a systematic way of looking at the universe. And we're going to learn about the method that scientists use to come to new information that can be considered scientifically sound. So science, like we said, is just a way of building and organizing knowledge based on testable explanations and predictions about the universe. So in short, we're just making explanations based on what we observe. And we didn't always used to do this. So back in the day, they used something called deductive reasoning. So we're going to base our conclusion or our answer to a problem based on information we already have. So because this is true, then this other thing over here must also be true. So if you ever have seen Sherlock Holmes or anything like that, he uses deductive reasoning. But you know, Sherlock Holmes usually gets his guy, so it must be good, right? Well, an example of deductive reasoning is on our slide. So if you go with the assumption that girls like chocolate, so in your experience, that's what it is. Girls like chocolate. Miss Vance is a girl. Therefore, she must like chocolate. Well, that's true, right? So your deductive reasoning worked, but do all girls like chocolate? Is that a correct assumption? So that's the problem with deductive reasoning here, is that if your assumptions are wrong, your conclusions are wrong too. So inductive reasoning is kind of the opposite. And this is where we aren't making any conclusions or answers to our problem until after we've gathered information and gotten our results. So for this one, if you wanted to know if Miss Vance liked chocolate, you might say, well, I saw that she has chocolate in her desk. I see her eating that chocolate, during class, and then she's always sharing candy with Miss Moore. So with all this evidence, I can come to the conclusion that just maybe Miss Vance likes chocolate. So with this method, this is more like what we do in science. So good science, we're going to use inductive, not deductive reasoning. So what happens if I don't have this information or these observations? So this is when we use the scientific method. So we use science. Okay, so the scientific method, it's not going to be like each scientist has a checklist and they do all of these things in the same exact order every time. These are guidelines that are generally used. So if you see an experimental setup, good science has used nearly all of these steps in one order or the other. Sometimes you got to stop and go back to the beginning, and that's fine. So the first thing we do is we state the problem. So why is something, maybe we want to ask why something's happening. Maybe there is something that needs to be fixed. So if there's a sports car that it stops working at a certain speed, well, that's a problem. And we need to use science to figure out how to fix it. And maybe there's a goal that needs to be achieved, like NASA wants to go to the moon or to Mars. So they need a special vehicle to do that. So we state our problem so that we know what direction our experiments should take. So the next thing we need to do is to gather information, because there's nothing new under the sun. So chances are someone has had either the same question as you or a similar question as you, and you're gonna be able to get that good background information, or maybe for your purposes, you don't even need to run the experiment because they've already done all that work for you. So maybe you'll be able to find other potential problems, like things to take into consideration when you're doing your experiment. So it's important that you gather this information, and it also helps you build your hypothesis. So you know what even you need to expect to happen. So a hypothesis, all that is a possible explanation for the problem that you have using what you know and observe. So you can call this an educated guess, but it's going to be a little more built up than that. You can't just take a full stab in the dark. Hopefully by the time you're making a hypothesis, you have a little more information than that. But you use your hypothesis as a claim later on. Oh dear, we're getting into CER, so make a little note by that, because your hypothesis and your conclusion, that's your claim. Pro tip. Okay, so writing a hypothesis, we're going to hit this really hard in a future lesson, but for today, just know that you got to identify your independent and dependent variables and identify your control. So writing a hypothesis is always going to be if the independent variable, then the dependent variable, then the control. That's why it's all big and bold. Highlight it, write it down, whatever you got to do. For the purposes of our class, this is how you form a hypothesis. When you get into higher level science, like my AP kids, hypothesis means something a little bit different, and so theirs are a little bit different, but don't panic. This is all you need to know on this slide, okay? So after we form a hypothesis, we have to test it. So we mentioned these variables, and like I said, we're going to talk more about these in depth in another video, but you need to know that dependent variables are what you're measuring, so it's your results, okay, are your dependent variables. And then independent variable is something that you change or that you're testing. So it's the thing that has the effect. So if your question is, does sunlight have an effect on whatever, sunlight is your independent variable. So now there's something called constants. So what a constant is the word constant means it doesn't change. So each test group gets the exact same thing. So what I'm trying to do is make sure that only the independent variable is having a result. It's the only thing changing things. So if I want to know if sunlight has an effect on how tall a plant will grow, I need to make sure that they're all getting the same water, the same dirt, the same seeds, so I know it was just the sunlight causing the change, okay? So controls. Students often get constant and control mixed up. A constant is the same for every single test group, okay? So our plants all got the same water, they all got the same soil. My control is what I'm comparing my results against. So how do I know if sunlight has an effect? Well, I gotta have one without sunlight, so that's my control. The control group is what I compare against. The constants are the things that all stay the same. After we have gotten our results, we're going to analyze the data. So if you are doing any kind of activity or experiment for me, you should have some kind of data table, and you should be recording your results as you go. Under no circumstance should I see a group frantically sitting there writing random numbers down on the paper because the bell's about to ring. So you should have good data results that you have recorded, and you're not going to be proving your hypothesis correct or incorrect at this step. So if I ask you to design an experiment, which, hint, hint, I am going to ask you to design an experiment, when you're at your analyzing data step, you should not be telling me whether you were right or wrong. You should only be describing patterns or observations, not telling me what those mean just yet. So this might be where you make a graph. This might be where you talk about how when one increased, the other increased. That could go in analyzing data. And so that brings us to the last bit, is drawing a conclusion. So here you're going, this is where you finally decide if your hypothesis was correct. And your conclusion, so whatever you write in your conclusion, it needs to be based off of your data, okay? Has to be based off your data. And it also has to be in CER format. Remember when I said that your hypothesis was a claim? Oh, so I should be seeing in your draw and conclusion part, there should be a CER paragraph. So if your data doesn't support your hypothesis, you make a new hypothesis and try again. So let's see if I can get my Apple Pen to work. So what I should see on your conclusion, I should see a hypothesis for my claim, evidence, this should be data. I should see for your evidence on your CER for your conclusion, there should be numbers, some kind of data from your experiment. So a number would be great. So if you did the plant experiment, I should see for your evidence. So hypothesis would be sunlight does have an effect on a plant. Then your evidence would be like the plants with the most sunlight got, 5 hours of sunlight and it grew so many inches. And then your reasoning, you are reasoning, explain the data. Okay, let me move my face. I know this is a little rough. So hypothesis is your claim, evidence is your data, and then your reasoning should be where you explain your data. So that's what goes in your conclusion. I hope y'all are taking notes because like I said, you're going to be asked to design your own experiment. We'll talk a little bit more about that later. I hope this was a good refresher course. If you have any questions or are still confused, please get in the Google chat and let me know. And I hope you guys have a good day.